Three-phase motors are self-starting due to a few key design features. Firstly, centrifugal switches are embedded in the motor's windings. When the motor starts, its rotating magnetic field induces a current in the switch. This current creates a magnetic field that interacts with the motor's main field, providing an additional torque to overcome starting inertia. As the motor gains speed, the centrifugal force activates the switch, disconnecting the starting capacitor and connecting the main windings directly to the power supply. Secondly, capacitor-start motors employ a starting capacitor connected in series with one of the motor's windings. During starting, the capacitor shifts the phase of the voltage applied to that winding, creating a rotating magnetic field. When the motor reaches a certain speed, a centrifugal switch disconnects the capacitor, leaving the motor running on three-phase power. Thirdly, capacitor-run motors use a capacitor connected in parallel with one of the motor's windings. The capacitor creates a phase shift in the voltage applied to that winding, producing a rotating magnetic field that keeps the motor running. Fourthly, permanent magnet motors contain permanent magnets that provide the initial starting torque. When the motor is connected to the power supply, the alternating current in the windings interacts with a permanent magnetic field, creating a rotating magnetic field that drives the motor. Additional factors contribute to the self-starting capability, including high starting torque, which is designed to overcome the inertia of the load being driven. Low starting current limits the surge of current drawn from the power supply during startup. Adequate winding resistance prevents excessive starting current and overheating. A properly designed square cage rotor allows for the induction of currents that create the starting torque. In more detail, the rotating magnetic field in a three-phase motor is crucial for its self-starting capability. This rotating field is established by the three phases of alternating current, each offset by 120 degrees. This phase difference ensures that the magnetic field produced by the stator windings rotates around the rotor, creating a continuous torque that initiates the motor's rotation. The interaction between the rotating magnetic field and the rotor is fundamental to the motor's operation. The rotor, typically a square cage design, consists of conductive bars connected by end rings. As the rotating magnetic field sweeps across these bars, it induces a current within them according to Faraday's law of electromagnetic induction. This induced current, in turn, generates its own magnetic field. The interaction between the stator's rotating magnetic field and the rotor's induced magnetic field produces a torque that drives the rotor. The magnitude of this torque is proportional to the strength of the magnetic fields and the phase angle between them. The square cage rotor design is particularly effective for self-starting due to its simplicity and robustness. The conductive bars provide a low resistance path for the induced current, allowing for a large current to flow and generate a strong magnetic field. This strong field interacts with the stator's rotating field to produce a substantial starting torque. Furthermore, the square cage design does not require external connections or slip rings, making it reliable and maintenance-free. Centrifugal switches play a significant role in the starting process of some three-phase motors, particularly capacitor-start induction-run motors. These switches are mechanically linked to the motor's shaft and are designed to open or close based on the motor's rotational speed. During startup, the centrifugal switch is typically closed, allowing current to flow through an auxiliary winding that is connected in series with a capacitor. This capacitor creates a phase shift between the current in the auxiliary winding and the current in the main winding, resulting in a higher starting torque. As the motor accelerates and reaches a predetermined speed, the centrifugal switch opens, disconnecting the auxiliary winding and the capacitor from the circuit. This transition allows the motor to operate more efficiently at its rated speed, as the auxiliary winding is no longer needed to provide additional torque. The design of the centrifugal switch is critical for ensuring reliable starting and efficient operation of the motor. The switch must be calibrated to open at the appropriate speed to avoid overstressing the auxiliary winding or causing the motor to operate inefficiently. Capacitor-start motors utilize a capacitor in series with the starting winding to create a phase difference between the currents in the starting and running windings. This phase difference generates a rotating magnetic field that provides high starting torque. The capacitor is typically disconnected by a centrifugal switch once the motor reaches a certain speed. Capacitor-run motors, on the other hand, use a capacitor in series with one of the windings to improve the motor's running characteristics. This capacitor helps to balance the voltages and currents in the windings, resulting in improved efficiency and power factor. The capacitor remains connected during normal operation. Permanent magnet motors incorporate permanent magnets in the rotor to create a magnetic field that interacts with the stator windings. This interaction produces torque and drives the motor. Permanent magnet motors offer several advantages, including high efficiency, high power density, and good dynamic performance. They are commonly used in applications where precise speed and torque control are required. High starting torque is essential for a three-phase motor to overcome the inertia of the load and begin rotating. The starting torque must be sufficient to accelerate the load from standstill to its operating speed. Factors that affect starting torque include the motor's design, the supply voltage, and the load characteristics. Low starting current is desirable to minimize the stress on the power supply and avoid voltage dips. High starting currents can cause nuisance tripping of circuit breakers and other protective devices. Motor design and control techniques can be employed to reduce starting current. Adequate winding resistance is necessary to limit the current flow through the motor windings, especially during startup. Excessive current can cause overheating and damage to the windings. The winding resistance is determined by the material, cross-sectional area, and length of the winding conductors. The square cage rotor design is a key feature of many three-phase motors. The rotor consists of conductive bars embedded in a laminated steel core. These bars are connected at both ends by end rings forming a closed circuit. When the stator windings are energized, they create a rotating magnetic field that induces currents in the rotor bars. These induced currents produce a magnetic field that interacts with the stator field, resulting in torque and rotation. The square cage design is simple, robust, and efficient, making it a popular choice for a wide range of applications. Understanding the principles behind three-phase motor self-starting involves considering several aspects of motor design and operation. The interaction between the stator and rotor magnetic fields, the role of capacitors and centrifugal switches, and the importance of high starting torque and low starting current are all essential elements. By carefully considering these factors, engineers can design and select three-phase motors that meet the specific requirements of their applications. The rotating magnetic field is the core principle behind how a three-phase induction motor self-starts. The three phases of alternating current, each separated by 120 degrees, create a rotating magnetic field in the stator winding. This rotating field sweeps across the rotor conductors, inducing a voltage and current in them. The induced current in the rotor conductors creates its own magnetic field. The interaction between the rotating stator field and the induced rotor field produces a torque, causing the rotor to rotate. The speed of the rotating magnetic field, known as the synchronous speed, is determined by the frequency of the alternating current and the number of poles in the stator windings. The rotor speed is slightly less than the synchronous speed, with the difference being called slip. The slip is necessary for the induction of current in the rotor conductors. The amount of torque produced by the motor is proportional to the slip and the strength of the magnetic fields. The square cage rotor is a common design used in three-phase induction motors. It consists of conductive bars embedded in a laminated steel core, with the bars connected at each end by end rings. The square cage design provides a low resistance path for the induced current, allowing for high torque production. The rotor bars are typically skewed to reduce noise and vibration. The design of the square cage rotor can be optimized for different applications, such as high starting torque or high efficiency. Centrifugal switches are used in some three-phase induction motors to disconnect the starting winding after the motor has reached a certain speed. This starting winding is designed to provide high starting torque, but it is not efficient for continuous operation. The centrifugal switch is mechanically linked to the motor shaft and opens when the motor reaches approximately 75% of its rated speed. Disconnecting the starting winding improves the motor's efficiency and reduces heat generation. Capacitor start motors use a capacitor in series with the starting winding to create a larger phase difference between the currents in the starting and running windings. This larger phase difference results in a higher starting torque compared to a motor without a capacitor. The capacitor is typically disconnected by a centrifugal switch after the motor has reached a certain speed. Capacitor-run motors use a capacitor in series with one of the windings to improve the motor's running characteristics such as power factor and efficiency. The capacitor remains connected during normal operation and does not require a centrifugal switch. Permanent magnet synchronous motors use permanent magnets in the rotor to create a constant magnetic field. The stator windings are energized with three-phase alternating current to create a rotating magnetic field that interacts with the rotor's magnetic field, causing the rotor to rotate. Permanent magnet synchronous motors offer high efficiency and precise speed control. High starting torque is essential for applications where the motor must start under load or accelerate a heavy load quickly. Factors that affect starting torque include the motor design, the applied voltage, and the load inertia. Motor designs with a high resistance rotor or a starting winding with a capacitor can provide high starting torque. Low starting current is desirable to minimize voltage dips in the power supply and reduce stress on the motor windings. Motor designs with a low resistance rotor or a starting winding with an autotransformer can help to reduce starting current. Variable frequency drives can also be used to reduce starting current by gradually increasing the motor's voltage and frequency. Adequate winding resistance is necessary to prevent excessive current flow through the motor windings, which can lead to overheating and damage. The winding resistance is determined by the material cross-sectional area and length of the winding conductors. The winding insulation must also be able to withstand the operating voltage and temperature. Proper motor selection and application are crucial for ensuring reliable and efficient operation. Factors to consider include the motor's horsepower, speed, torque, voltage, current, efficiency, and enclosure type. The motor must be sized appropriately for the load to avoid overloading or underloading. The motor's operating environment must also be considered, as temperature, humidity, and contaminants can affect its performance and lifespan. Regular maintenance, such as lubrication, cleaning, and inspection, can help to extend the motor's lifespan and prevent failures. Understanding the specific characteristics of different three-phase motor designs allows for optimized application. Motors can be chosen for specific jobs because of how they are designed. For example, permanent magnet motors are often picked for high-precision applications but are typically avoided in high-inductive load applications since permanent magnet motors have little to no start-up torque.